Hey everyone, Mrs. Ragstad here. This is video 9-2 on temperature, pressure, and volume. And the objectives of this lesson are to be able to state the freezing and boiling points of water, both in Fahrenheit and Celsius, and also to describe the relationship between pressure and temperature, and volume and pressure, and volume and temperature when it comes to gases. I also need you to know the most important units that we use for pressure and for volume. Let's talk about temperature. We've already talked some about temperature in our unit on convection, conduction, and radiation. So you probably remember that temperature is the average kinetic energy of the atoms or molecules in a substance. And over here I put a little cartoon of a Erlenmeyer flask with the atoms drawn out, and you can see that they are in motion, they're moving really fast, and they are bouncing against the edges of the container. The temperature translates to, if you took the kinetic energy of the motion of each one of these molecules or atoms and found the average of it, because you can see they're not all moving at the same speed. Some of them are going really fast, some are going really slow. And that average, we would view it as temperature. All right, so there are several different units that we can use to measure temperature. The first one that we're most familiar with is Fahrenheit, and we say degrees Fahrenheit. So you can see that it would have the little degree sign. So room temperature is about 70 degrees Fahrenheit. And you can see these are several common temperatures that we might be familiar with. So baking cookies at 350 degrees Fahrenheit in the oven. Water boils at 212 degrees Fahrenheit. That one you need to memorize. Alcohol boils at a much lower temperature at 172 degrees Fahrenheit. So that's why sometimes people use alcohol in cooking and it will boil off in the process of cooking. So it leaves the flavor but not the alcohol. The freezing point of water is at 32 degrees Fahrenheit. Another one you need to memorize. Mercury freezes and melts at negative 38 degrees Fahrenheit, which is pretty cold. Mercury is actually a liquid at room temperature, which is kind of fun. Dry ice, which is something you might have had the opportunity to interact with, freezes at a negative 109 degrees Fahrenheit, which is why it is very, dangerous to touch it with your bare hands, because you can actually give yourself a frostbite or a kind of freezer burn. And there's also liquid nitrogen, which is something that's also kind of fun to play with, negative 320 degrees Fahrenheit. So liquid nitrogen is very, very, very cold. I remember in college, a lot of people at my school had the tradition of freezing pumpkins on Halloween in liquid nitrogen and throwing them over the edge of a tall building, and rumor had it that you could see a blue flash when it broke into a million pieces at the bottom. This is also some kinds of ice cream are made with liquid nitrogen. I believe A La Minute, our favorite little specialty ice cream shop in downtown Redlands, uses liquid nitrogen in order to freeze the cream. So that's another fun fact. And then absolute zero is at negative 459.7 degrees Fahrenheit. Absolute zero is a temperature we can't actually get to. It's the temperature at which all molecular motion stops. And as far as we know, this can't really happen. It's impossible to happen. And so scientists have been able to achieve temperatures that are slightly above absolute zero, but not actually absolute zero. The temperature in outer space is supposed to be about 3 degrees above absolute zero. So the other scales that you need to be familiar with are Celsius, which is considered a metric unit that's more user-friendly. Most countries of the world use this in everyday life. You need to know that water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. In fact, the Celsius scale was kind of built around the freezing points and boiling points of water, which makes it really easy to remember. And here are the other reference points of these much more familiar temperatures. And finally, we have the Kelvin scale. And for Kelvin, we don't use the degree sign. We do for Celsius and Fahrenheit. And the cool thing about Kelvin is that there are no negatives. So in other words, Kelvin is actually built around the concept of absolute zero, because 0 Kelvin is absolute zero, the temperature at which all molecular motion stops. So at absolute zero, this picture over here would not have these atoms flying all over the place. They would literally stop moving altogether, which is theoretically impossible. Okay, next we're going to talk about pressure. And pressure has to do with the force that molecules put on the side of a container, or collisions. So over here I have this cube where there are, again, atoms flying all over the place because they're a gas. And as they're flying, because they have a certain temperature, right? They have an average kinetic energy. They're hitting the sides of the walls. And the harder they hit the sides of the walls, the more pressure there is. So you might be familiar with pressure in terms of pressure cooking, or if you have an Instapot. I have one, and you have to be very careful to not let the pressure release too soon, because it could cause the lid to fly off. So pressure has to do with molecular collisions with these atoms hitting the side of the container. Now, pressure also has to do with differences in pressure. When there are differences in pressure, then fluids move. So when there are pressure differences, then fluids move. And remember, fluids can be a liquid or a gas. And so you've probably experienced this in everyday life, if you've ever drinking something out of a straw. So if you have a straw in your mouth, but you are not sucking on it at all, you're just kind of leaving it be, no liquid is going to go up into your mouth, because the pressure that the atmosphere has. Now remember, there's air all around us, right? So even though it looks like there's nothing around me, there is. And you can feel the air molecules that are around you because I'm putting pressure on them. I can feel them like wind. So the air molecules are actually pushing down on your liquid with a certain amount of pressure, because there's miles and miles of air above us, right? So that's putting weight on all of us. And as long as there's the same air pressure inside of the straw as outside of the straw, no liquid is going to go into your mouth. However, if you create a vacuum in here, if you suck the air out of the straw, then you create a difference in pressure, because the pressure inside of the straw is basically zero. If you have a vacuum, if you have nothing in it, no molecules, then the pressure is zero. But the pressure on the outside is still atmospheric pressure. And what happens is the atmosphere pushes down on the liquid, and that creates a space and a force for this liquid to move up and into your mouth. So that's a little experiment that you can try at home. Another instance where you might have differences in pressure causing fluids to flow would be with the wind. And I experienced this over spring break when I was in Palm Springs, where it was very windy. So if you have areas of high pressure with the atmosphere and areas of low pressure, it's going to cause the air to move, which is the wind. And you might hear weather people talking about this on TV when they're giving the forecast. When you have high pressure and low pressure is what causes air to move, or wind. All right, last but not least, we're going to talk about volume. And we're already somewhat familiar with volume because it's how much space something takes up. And we know some formulas for volume, right? We know length times width times height, and which is the formula for the volume of a box, and also for a cylinder, pi times the radius squared times the height. And for math, I believe you know the formulas for some other shapes as well. Well, we're going to see in this unit that the temperature and the pressure of any gas has an effect on the volume. So for example, I have just some example balloons right here, and each balloon has a certain amount of space that it's taking up. But if I were to put this balloon into very, very warm water that was almost boiling, the balloon is going to expand, right? Because each of these molecules or atoms is going to start moving faster and faster and faster. Therefore, it's going to hit the sides of the container faster and faster. And in the case of a balloon where it's expandable, to accommodate that, the volume is going to increase to try to outdo some of the pressure. So you can see that pressure, temperature, and volume are all interrelated and interconnected. Likewise, if I took one of these balloons and I suddenly immersed it in ice water, all these molecules would start moving more slowly and they would not hit the sides of the balloon quite as hard. And so what would happen, take a guess, that balloon is going to shrink and shrivel up until it gets heated up again, because there's the same number of molecules in the balloon, but they don't have the same amount of energy because they've been cooled down. So in this unit, you're going to be doing a virtual lab to explore those relationships between pressure and temperature and volume and how they're all related to one another. And I will see you guys in the next video.